Assalamualaikum warahmatullahi wabarakatuh. First, for introduction, I would like to explain the unified CAD and CAM platform. CATIA combines design, manufacturing, and inspection into one integrated system. The first stage is 3D modeling, where we create the product model with accurate dimension and geometry. Next is CNC toolpath, where CATIA generate the machining path and cutting operation for the CNC machine. And finally, simulation and audit are carried out to verify the machining process, detect possible error, and ensure the product meets the required quality before actual production. Next is the slide show the machining sequence used in our project. The first process is roughing, where large amount of material are removed quickly to form the basic shape of the workpiece. Next is pocketing, which create internal cavities and remove material from selected area. The third process is profile, where the cutting tool follow the outer contour to produce the final shape and dimension. Finally, auditing is performed to inspect the finished part, verify dimensional accuracy, and ensure that the machining process is complete successfully. And last, our project has two main objectives. The first objective is optimize CNC programming. By using CATIA, we can generate efficient toolpath, reduce machining time, improve cutting efficiency, and minimize programming error. And the next one is quality assurance and metrology. After machining, inspection is carried out to ensure the final product meet the required dimension and quality standard. This helps reduce defect and improve production reliability. In conclusion, the CATIA CAD and CAM process integrate design, machining, and inspection into one workflow. This improves productivity, machining accuracy, and product quality when reducing manufacturing time and error.
Assalamualaikum and good day everyone. So in this section, I will explain the methodology used to complete our CAD-CAM project using CATIA software. So the first step, as we can see, part design preparation. First, we create a 3D model of the workpiece using the CATIA part design workbench. So every feature, including the pocket, hole, curved surface, and dimension, was designed according to the engineering drawing provided. After complete the model, we checked that all features were fully constrained and free from design error before moving to the machining stage. And second, we creating the stock. The stock represents the raw material before machining begins. It was created slightly larger than the final workpiece to allow enough material for the cutting process. This enabled CATIA to simulate how material is removed throughout the machining operation. And step number 3, create the exist system, as we can see. After define the stock, we create the exist system to establish the machining reference point and determines the orientation of the workpiece. We ensure that the z-axis pointed upward, which represent the cutting tool approach direction, and the coordinate system was correctly configured. And for the fourth step, we create the tool reference plane in a separate part design file. This plane serves as the approach and retract position for the cutting tool. An exit system was also defined on the plane before assembling them with the workpiece using the assembly workbench. This ensures safe tool movement during machining. And step number 5, we can see advanced machining setup. So once the model was ready, we switched to the advanced machining. So we can define the machining setup by selecting the machine tool, workpiece coordinate system, stock material, and the final part geometry. This setup forms the foundation for generating accurate machining operation. And number 6, we can see cutting tool selection. So next, we select the suitable cutting tool based on each machining operation. The tool used were included 63 mm face mill for facing, 12 mm and 8 mm end mill for roughing, pocketing, and contouring, 10 mm ball end mill for surface finishing, and a 6.8 mm drill for hole machining. Appropriate cutting parameters such as spindle speed, feed rate, cutting depth, and step over were assigned to each tool. And number 7 were tool path generation. The machining operation were then programmed in sequence. The process began with facing to create a flat surface, followed by roughing to remove excess material. Pocketing and profile contouring were performed to produce the required shape, followed by isoparametric finishing to achieve a smooth surface. Finally, drilling was carried out to create the required hole. And number 8 is machining simulation. After generate all to pulp, we ran the machining simulation in CATIA. The simulation verified the machining sequence, tool movement, and tool change while checking for any possible collision or machining error. Any issue detected were corrected before proceeding. And lastly, final verification. We evaluate the machining result using CATIA's analysis tool. We perform remaining material analysis to identify any material left after machining and gauge analysis to detect overcutting or tool interference. The machine model was then compared with the original CAD model to verify dimensional accuracy and confirm that machining process was successfully completed. So that concludes the methodology of our CAD CAM project. Thank you for your time. I will pass to next person.
Assalamualaikum warahmatullahi wabarakatuh. My name is Fahrin Ryan bin Hamdan, and today I will present about result and discussion for our CAD-CAM project. So without further ado, let's jump right into it. First of all, in this section, I will explain about the final result of our project, the machining simulation part, the comparison in CATIA, and issues encountered that in the simulation. To do the comparison, run the analyze feature in CATIA, and there will be analysis that we can do, which is the remaining material analysis and the gauge analysis. Okay, so this is the result that we obtain after the machining simulation. The manufacturing program was successfully conducted, consisting of 5 tool changes. We start off with face mill to do the facing, the end mill with 12 diameter for roughing, pocketing, and profile contouring. End mill 8 diameter 8 to do the pillars, as you can see here, the pillars pocketing and the 4 pillars here. And drill was used to drill the holes inside the pillars. Was assigned, we need to do 6 process, so we have the facing, the roughing, pocketing, profile contouring, the ball mill diameter 10 for isoparametric, and the drilling. So we have 6 process that we did as we were assigned by our lecturer, Mr. Shafiq. While remaining material analysis, okay. So to do this, there's a feature in CATIA during simulation here. There is a button here where you can analyze. First, the green indicates horizontal faces and internal pocket walls reach perfect dimension within the tolerance, which is 0.01 millimeter. So as you can see here, this is our part, this is our stock. All the green are in perfect dimension. The light blue indicates minor excess remaining material ranging between 0.01 to 0.02 millimeter along the outer sweeping contour. So here, as you can see, there is a little bit of bluish, light bluish excess. So this is the excess of remaining material for between 0.01 to 0.02 millimeter tolerance. Light blue regions at the bottom of the part represent the product's remaining raw stock material. So, okay, maximum material deviation, specific areas exceeding 0.02 tolerance limit visible along the outer perimeter wall profile indicates in dark blue. Next is the gauge analysis. So here is the parts, the green parts. First of all, let's see like the top faces and internal pockets are highlighted in green. So as you can see, most of the parts here, majority of the color is green, which is completely safe and within correct dimension and within tolerance. The outer vertical walls of the 4 corner cylindrical pillars display a brown color. If you look closely here, all 4 of these have brown color, and it's indicating a critical issue, which is the tool overcut directly into the intended part geometry. So it's get a little bit deeper between 0.01 to 0.02 millimeter or worse. So this is discussion, which is the issues that we encountered. Okay, the outer sweeping walls that we set here. the auto shaping walls here that have minor excess left of the remaining material. Attribute to the stopover and scallop height limitations within the isoperimetric machining operations. The tool step down was likely too large to smoothly blend along the complex vertical curvatures, leaving behind physical scallop ridges of material. So maybe our cutting tool that we were using is too big. And to resolve this, the actual step down and radial step over parameter must be decreased in the finished machining setting, or a 2D contour profiling path should be introduced using a smaller end mill to clean up parameters. So next, we have the gauge issues. So the external vertical cylindrical faces of the four pillars basically, conforming a negative deviation, the gauge exceeding the gauge exceeding 0.01 millimeter tolerance indicates that the cutting tool invaded the boundary of the part, and typically occurs in CATIA cam when there is an incorrect tool radius compensation setting or an improper guide curve selection in the isoparametric workbench, resulting the tool exists to lean slightly into the pillar geometry during tight cornering transitions. This can be corrected by verifying the tool offset parameters, ensuring it is active and accurately matched to the tool resource geometry, and rechecking that the pillar faces are correctly designated as check surface in the software. So it's either we reset the offset parameters, or we can use the check features when we were doing the profile contours to encounter to what we call that, to overcome the issues. So that is all from me. Thank you for watching my part, and I will pass down to the next presenter, who I believe is Akmal. So see you next time.
Assalamualaikum. Today I want to present about a conclusion on my project. Firstly, the key achievement success a 3D printed piece using CATIA, because usually printing 3D printer design specification. In addition, the full machining process was developed using the advanced machining workbench, which allow proper planning of the part and machining operation. The machining simulation was carried out success and had verified entire process before actual manufacturing. This step is very determined reduce error and improvement efficient. In terms of result, most switches such as black surface, pocket, and hole were produced within suitable tolerance level. Overall, the interaction between CAD and CAM is successfully achieved, and the workflow designed to manufacturing simulation was complete smoothly. Next, finding and recommendation. Find the recommendation several manual issues were identified the machining simulation. They include small error, curve, and surface as the slight increase at the pillar base area. In addition, some remaining material was observed, which was mainly caused by relation height step over and step down value during machining. There was also slight overcut on cylindrical surface, and this issue linked to interact to reduce operation setting. To improve the issue several recognition. Firstly, reduce the step over and step down value will help improve machining accuracy and surface quality. Secondly, using smaller finishing tool is recommended to achieve a smooth surface. We need explicitly complex geometry. Lastly, to compression settings should be properly adjusted and optimized to ensure better dimension accuracy in future machining process. Thank you from me.